Imagine a stream of air. Nothing blocks it. Nothing pushes it sideways. So, it should travel in a perfectly straight line. But that's not what happens. Every weather map on Earth tells a different story. Jet streams bend across continents. Trade winds curve over the oceans. Hurricanes spin with incredible power. Even aircraft flying thousands of kilometers slowly drift off course. So, what is changing their direction? Is there an invisible force pushing everything sideways? For nearly 2 centuries, scientists have known this phenomenon as the Coriolis Effect. But here's the twist. No force is actually pushing the air sideways. The air is still moving in a straight line. The real culprit is something far more surprising. Welcome to Earth Diary. To understand why, let's begin with a simple experiment. Imagine you're sitting opposite your friend on a merry-go-round. You throw a ball. When the platform isn't moving, the ball travels in a straight line and reaches your friend perfectly. Now the merry-go-round starts spinning. You throw the ball again. Exactly the same way. But this time, your friend sees the ball curve to the right. Did the ball actually change direction? No. To an observer watching from above, the ball never curved at all. It traveled in a perfectly straight line. The only thing that changed was the merry-go-round. While the ball was in the air, the platform and your friend rotated beneath it. This apparent deflection is called the Coriolis Effect. It is the apparent change in the path of a freely moving object caused by the rotation of the surface beneath it. In meteorology, this apparent effect is commonly called the Coriolis force. Now replace the merry-go-round with something much bigger. Earth. Every second, our planet spins from west to east. At the equator, that rotation reaches nearly 1,670 kilometers per hour. We're moving with Earth, so we never notice it. But the atmosphere is moving too. Whenever air travels over long distances, Earth continues rotating beneath it. To us, the air appears to change direction. Viewed from above the North Pole, our planet spins counterclockwise. From space, the air is still moving in a straight line. But because Earth is rotating beneath it, the air appears to drift to the right of its intended path. This is why, in the Northern Hemisphere, the Coriolis effect causes moving air to appear to deflect to the right. Now, let's look at the other side of the planet. Viewed from above the South Pole, Earth appears to spin clockwise. Once again, the air continues moving in a straight line. But now, on Earth's surface, air drifts to the left of its intended path. This is why, in the Southern Hemisphere, the Coriolis effect causes moving air to appear to deflect to the left. So, is the Coriolis effect the same everywhere on Earth? Let's put it to the test. Imagine 3 identical airplanes taking off at exactly the same speed. One flies near the equator. One flies at 30 degrees latitude. And one flies near the North Pole. Which one will appear to change direction the most? Most people would say they should all deflect equally. But they don't. The airplane near the equator barely changes direction. The one at 30 degrees latitude deflects a little more. And the airplane near the pole experiences the greatest apparent deflection. Because the Coriolis effect depends on latitude. At the equator, it's essentially zero. As you move toward the poles, it becomes stronger and stronger, reaching its maximum at the North and South poles. But latitude isn't the only thing that matters. There's another variable. Speed. The faster something moves, the stronger the Coriolis effect becomes. Fast jet streams, aircraft, ocean currents. These all experience much greater apparent deflection than slow-moving objects. In the 1890s, Norwegian explorer Fridtjof Nansen was drifting through the Arctic, studying ocean currents. He noticed something strange. The ice wasn't drifting in the same direction as the wind pushing it. It drifted consistently off to the side, 20 to 40 degrees to the right of the wind. Nansen couldn't explain it. So he brought the problem to a physicist named Van Walfrid Ekman. Ekman worked out the answer. Earth's rotation wasn't just bending air. It was bending entire ocean currents in a spiraling pattern now called the Ekman spiral. The same invisible effect, from a merry-go-round to the atmosphere to entire ocean currents. You've probably heard that the Coriolis force determines which way water drains in a sink. It doesn't. Over such tiny distances, the effect is far too weak. Only when air and water travel hundreds or even thousands of kilometers does Earth's rotation become impossible to ignore. But here's another mystery. If the Coriolis force keeps pushing moving air sideways, why don't winds just keep turning forever? Imagine a parcel of air high above Earth's surface. A pressure difference pushes it northward. But the moment it starts moving, the Coriolis effect begins bending it to the right. As the wind becomes faster, the Coriolis effect becomes stronger. So should the wind eventually make a complete circle? Surprisingly, it doesn't. Eventually, two invisible forces become perfectly balanced. The pressure gradient force continues pulling the air toward lower pressure. At exactly the same time, the Coriolis effect deflects it sideways with equal strength. Neither force wins. Instead, the wind slips between them. It now flows almost perfectly parallel to the isobars. Meteorologists call this remarkable balance geostrophic wind. And this simple balance helps explain why winds high in the atmosphere can flow parallel to isobars. But this isn't the end of the story. Earth's atmospheric circulation is far more complex than this simple balance. The Coriolis effect is only one piece of a much bigger puzzle. So, if you enjoyed this journey into the science of our atmosphere, don't forget to like this video, subscribe to Earth Diary, and ring the bell so you never miss an episode. Until next time, keep exploring.